Good morning. I'm Nadia Kozachenko. I'm a teacher of Kryvyi Rih State Pedagogical University. My research area is logic and its application. So I always deal with model, which can have different levels of rationality, of formality. The standard approach to teaching modeling and its application is moving between two levels, theoretical and empirical. Indeed, the model emerges as an idealization of practical experience. The further process is a gradual refinement of the model based on practice. But often we adjust the practical implementation to the requirements of the model. Thus, quite often we believe that the theoretical structure is stronger, more important than the nuances of practical implementation. Empirical process always involves errors, but quite often it is difficult to distinguish between the error of empirical process and the real inconsistency of the process with the model. But empirical refinements are not the only way to improve the model. The theory really has its own patterns and allows us to refine itself. But in addition, the theory can be improved and even checked by comparing it with other theories. It can be done by at least two ways. The first way, by harmonizing it with another theory, which has a confirmed status. The second way, by considering the theory within the framework of a more formal system, which has the proven status. So, we want to show how it works. We will deal with so-called belief revision, the general framework for modeling of reasoning. The basic ideas described in this approach are constantly used in fields of databases, functioning, support, and updating, software products update and consolidation, and other. AGM is one of the more formal parts of belief revision. AGM is a system of principles for describing of belief changes. It is often seen as a branch of epistemic or doxastic logic. AGM is an attempt to approach to modeling of real reasoning. There are presented general concepts of belief change and rational agents reasoning in AGM. Also, AGM defines main cognitive actions. We will consider only two of them, of these actions, expansion and contraction. They are considered the basic operation. The goal of our research. We will consider the epistemic system of AGM in which the main concepts of belief revision are formulated. This system is semi-formal. The principle of cognitive actions are formulated in it as general guidelines, which are not organized in strict formalism. So we will consider the concept of cognitive actions, their types, and some problems that concern researchers but do not receive a satisfactory solution. We will formulate the basic principle of interpretation of cognitive actions of AGM as doxastic modal operators of three-valued logic. And then we will check what properties the obtained operators exhibit, what regularities and connections exist between them, and how we can express the postulates of AGM cognitive operations in three-valued logic to obtain theorems. Obviously, we can use tables to validate their resulting expressions. Let's start. One of the founders of AGM, Peter Gärdenfors, formulated the system of main components of epistemic theory. They are epistemic states, epistemic attitudes, epistemic inputs, and criteria of rationality. Every epistemic theory is based on some basic concepts. First of them is belief. AGM is a sententional system. It considers every belief as a sentence. Thus, we can use proposition of logical language to represent belief. Then we will use a belief set. AGM uses a set theoretical notation for describing the relation between belief and belief set. So, belief belongs to the belief set if the agent believes in it. Belief set is considered closed under logical consequence. So we can put A derivable from K, belief set K, if and only if A belongs to belief set K. Then we have three statuses of belief. belief A is accepted if and only if sentence A belongs to belief set K. Belief A is rejected if and only if A doesn't belong to K. Also, the status of A is indeterminate. We will use a simple notation for doxastic and non-doxastic expressions. Plus means doxastic operator of expansion. Div means doxastic operator of contraction. So we choose the complete logical tree to translate main AGM principles. It is an ordinary three-valued logic developed by Lukasevich. In our main article, we explain the reason that allow us to use this logic. We leave the standard Lukasevich definitions of logical connectives, conjunction, disjunction, implication, and negation. In our presentation, we consider only tables for cognitive operators, which can be combined in doxastic and non-doxastic expressions. So, we are based on belief statuses and their relation to cognitive actions described by Gärdenfors. It allows us to also consider the idea of success in performing a cognitive action. A cognitive operator must return true if it changed the belief status according to Gärdenfors requirements. So, we have a table definition of expansion. We performed similar actions to obtain the tabular definition of the contraction operator. Like modal, unary operator in three-valued logic. So, with contraction operator, div, we can formulate the law of the excluded fourth, which exhaustively describes the set of possible statuses of a sentence with respect to the agent's belief set of beliefs. We can prove the corresponding theorem in L3 using a truth table. Thus, it looks we have chosen the correct interpretation of the operators. Moreover, it is noteworthy that the doxastic operators introduced in this way demonstrate significantly different properties. Plus A behaves like a normal modal operator and satisfies the corresponding properties. This operator also allows iteration and can be applied to the doxastic formulas. So we can successfully use expressions like plus, A, and other. In turn, the operator div, contraction operator, applied to doxastic formulas returns a contradictory formula. Both expansion and contraction deal with three values: true, indeterminate, false, and map them on two values, true or false. Thus, contraction applied to the formula with only T and F values without N gives us only false. And then we can describe all statuses of a proposition using our notation for doxastic action. So, the main part of our work consisted in the fact that using the obtained notation, we translated the postulates of AGM for cognitive actions into the postulates of doxastic unary operators within the framework of three-valued logic. This postulate describes the family of expansion operators. Factually, with the help of the postulate of expansion, the operator of expansion can be axiomatically defined. That is, if the doxastic operator satisfies the postulate of expansion, then it is equivalent to the operator expansion of AGM. We put this expression as follows. The upper expressions is the AGM postulate. The lower expression is its representation in logic L3. To formulate the corresponding expressions, we relied on the properties of doxastic operators defined above and on the behavior of truth values. Using truth tables, it is easy to show that all of them are theorems in L3. Indeed, the expansion operator behaves like a normal operator and does not cause any inconvenience being translated into three-valued logic. Moreover, all its properties were quite predictable. In turn, the contraction operator behaves differently. Thus, additional formalization are required to express the AGM postulates of contraction. Building a contraction operator is considered to be successful if it satisfies the postulates of contraction AGM. But expressing these postulates using our operator was not so easy. To get L3 tautologies, we had to strengthen the formulas by expansion operator. But these changes never went against the essence of the postulate. Indeed, we can obtain many interesting properties with these interpretations. Some of them are unexpected, but others even allow us to refine the properties of doxastic operations. Thus, we can say that our doxastic operators satisfy the basic properties of cognitive actions represented in Gärdenfors postulates. Moreover, we can express some additional properties of AGM cognitive actions by tautologies of L3. Really, we work with modal and other non-classical logic in the master's classes. We are dealing with formal systems and their properties. Most systems describe the process of modeling reasoning at a very high level of idealization, and it is quite difficult for master students to translate them into practical activity. To be honest, most of the master students don't perceive topics in modal or multi-valued logic as relevant to practice. The corresponding tasks are rather perceived as interesting but purely formal tasks. On the other hand, belief revision is perceived in a completely different way, since it is only partially formalized. It can be said to be a set of guidelines that everyday reasoning must follow to be considered rational. Such a semi-formal approach leads to the fact that systems based on belief revision are more closely related to practice, but do not have the proven characteristic of formal system. Therefore, they are easy to implement, but there is no guarantee that their requirements are consistent or complete. It is not enough to specify some such semi-formal system only based on practice. They should be coordinated with formal schemes of a higher level.